All right, let's look at this scenario here. We have two stacked blocks and they are being pushed across a horizontal surface. So there's an applied force F prime. So note that applied force in the diagram. Note where it's being applied as well. It's being applied to the lower block, the 3M block. Our givens for this problem are M, which allow us to know the masses of the blocks. Those are given in the diagram below. F prime, the applied force is a given, and then mu sub k. And let's talk about which mu sub k here that's given. This mu sub k is the coefficient of kinetic friction at this interface down here, the interface between the 3M block and the surface that it's sitting on. That's the mu k that's given. What we're asked to determine in this problem is the minimum coefficient of static friction for the interface between the blocks such that they do not slip with respect to one another. And we'll assume that the system accelerates to the right here. So the coefficient of static friction that we are looking for is this coefficient of static friction at this interface right there, the interface between the blocks. So when we're working with friction is always applied at an interface, right? It's really important to keep track of and stay organized about which interface you're discussing. And a problem like this is good because it introduces us to a situation where there's more than one interface. So we can't just make assumptions about what's going on here. So the idea is that this applied force is applied to the bottom block, but what we want there to be enough static friction between the blocks that the two blocks will accelerate together. So that's another piece, of course, that we're given here. We assume the system is accelerating to the right, so I'm going to put that somewhere in my diagram here, I guess, for my brain to be reminded that acceleration is to the right here. That's going to have an impact also on my coordinate system choice. So for a problem like this can be, it might feel a little bit overwhelming when you first look at it, that there's a fair amount going on. But like everything else, if we break this down systematically and science gives us structure to do this, this is I don't know, it's not as hard as it looks. So let's do that. How we do this for force analysis is, of course, through free body diagrams. So I'm going to start with the free body diagram for the 2M block, and then I'll also, of course, draw a free body diagram for the 3M block. Every object, every body in a problem that might have multiple bodies, remember that every body needs to be depicted separately on the free body diagram. That force of internal friction, the force of static friction that's at the interface between the two blocks, that is a force that's external to the blocks themselves. But if you looked at this as one system, if you tried to say, well, why can't I just draw one free body diagram for both the blocks here? You wouldn't be able to get at that static frictional force because that would be an internal force to the system. So that approach doesn't work for this problem. Okay, so maybe you're working ahead of me right now and you've got your free body diagrams. This is a good spot to pause the video and see how your force identification is going. That's a fundamental skill for all this is, can you identify the forces and then can you depict those on your free body diagram? So let's do that. If I look at the 2M block, what I know is I get my one invisible force, which is the weight of that block. So I can draw that in and I can either write W for weight there. Sometimes I'll do that. Or I can just go ahead and put in the magnitude of that weight right away. I'll leave that up to you guys. I will, for this particular version, I'll put in the magnitude of that block's weight, which is its mass multiplied by gravitational acceleration. So that's a downward force there, the one invisible force. Any other force on this block must be through contact. And the only thing that is in contact with the 2M block is it's only in contact with the block beneath it, the surface of the block beneath it. And surfaces, remember, can exert two types of forces. They can exert normal forces and frictional forces. So the surface, it's basically the top of the 3M block that's touching the bottom of the 2M block. That's exerting a couple different types of forces. One is a normal force, of course, that's normal to the surface. I'm going to call this N sub 2, 3, indicating that it's the normal force at the interface between the 2M and 3M block. And then, of course, we have frictional force. Now, we know that we're studying static friction at this particular interface because what we want here, the constraint that we're trying to make happen, is basically that we don't want the blocks to slip with respect to one another. So, our focus here then is on static friction, and then that's why we're looking for the coefficient of it. So, the big question then is what direction does static friction act for the 2M block? And I'm going to leave that for you to think about for just a moment. And then we'll move on to the 3M block, do some forces, and then we'll come back. So think about that. And as I'm moving ahead, if you haven't yet, just put down that static frictional force in a direction that makes sense to you for the 2M block. Moving ahead to the 3M block here, what do we have? Well, we know we have our one invisible force, which is the weight of the 3M block. That weight has a magnitude of the mass of the block multiplied by gravitational acceleration. So I've got weight on there. And then I can start looking at what's touching the 3M block, right? What's in contact with it? Well, we've got this applied force that's in contact with it. That might be calling out to me, right? That F prime, notice, is only in contact with the 3M block. So it must end up on the 3M blocks free body diagram. So I'm going to go ahead and place that on there. That one is a fairly sure bet, that F prime. Then that's a given. And then what else is touching the 3M block? Well, we have actually contact to the 3M block on three sides of it. On the left side by that F prime, if we look at the bottom of the 3M block, it's in contact with the surface beneath it. And what we're told is that there is a coefficient of kinetic friction at that surface. So we know that friction occurs at that interface. So again, still focusing on, let me highlight this. I'm focusing on this interface right now, okay, as we're talking. Focusing on the interface between the 3M block and the surface beneath it. And let's go back and talk about what forces are exerted at that interface. So there's a normal force that's exerted by the surface beneath the 3M block, and that's being exerted upward, normal to the surface. I'll call that N sub 3, as I'm not doing any analysis of the surface beneath there. And what else is going on? Well, I have the force of kinetic friction, and kinetic friction is one that is more straightforward than static in that most of the time, there are small exceptions, but most of the time, the force of kinetic friction, when we look at direction, we can just say the direction of kinetic friction is going to be to impede the motion. So in this case, we are told that the system starts from rest and we're going to accelerate to the right. Just kind of if you had two blocks and you pushed them with a pencil or something, you push the bottom block, what would happen? So my friction, my kinetic friction, I can say is going to be leftward, impeding the motion. Okay. Now, there's one more surface though that's in contact with the block, the 3M block, and that's the surface above it. So now let's go and talk about that surface. So let's take away this highlighting here. And now my focus is going to be on this interface, the interface between the two blocks, and thinking about what forces are there, right? So again, there are two forces that surfaces can exert: normal forces and frictional forces. So the normal force is often the easier one to figure out. The normal force is always normal to the surface. So on the 3M block, it is pushing downward. And we've done some stack blocks problems, so this shouldn't be too much of a shock to you. Downward, and that normal force is the normal force we're calling N23. So I want you to notice that these two forces, this downward N23 and upward N23, are part of a third law force pair. So that's Newton's third law showing up, as it does when we look at interactions. Okay, but we're not done with the surface between the blocks, are we? Let's, because what we've been kind of avoiding, and maybe now it's time to talk about it, is the static friction. So let's go back to the 2M block for a second. This might help to open this up a little bit. What direction is the force of static friction exerted in? That's where we left. That's the question that we left over here, kind of left that open. And hopefully by now you have a direction drawn in your diagram. So my question to you would be if when you're trying to figure this out, you can use Newton's second law, right? So what is that? Sum of forces equals mass times acceleration. I know that this 2m block will be accelerating to the right. So I know there has to be some net force to the right. And I know that that acceleration is always caused by a force. Accelerations don't just happen, right? Newton's first law. Accelerations are always a result of an applied force. So that force must be, that force of static friction must be to the right on the 2m block. And that is, in fact, the force that's responsible for accelerating that block as it accelerates to the right. Now, what that means is that that force of static friction there um, must be exerted in the opposite direction on the 3m block. I'm going to say that again. What that means is that that force of static friction must be exerted in the opposite direction for the 3m block. So actually for the 3m block, pointing to the left, I'll have force of static friction plus kinetic friction. And then what this gives me is another force pair. This static friction and this static friction is another third law force pair. And remember that when you're applying Newton's third law, the two forces that are part of a force pair, they will always appear on different free body diagrams because Newton's third law is about interactions. And they will always, of course, be equal and opposite. So if you're kind of testing to make sure that you really are representing your force pairs correctly, look at your free body diagrams, ask yourself, are they equal and opposite? Are they pointing in opposite directions on your free body diagram? And then they should never appear on the same free body diagram, of course. Okay, so yeah, I mean the first time you look at something like this, that often throws students as far as like, how can I figure out the direction of frictional force? So I tried to bring you through some of that as far as motivation when we're talking through here. Like I think it's easier to just analyze the 2m block to know that because it's accelerating to the right, the only available force that is responsible for the rightward acceleration of that block is going to be the static frictional force. I cannot put F prime on my free body diagram for the 2m block. I cannot. It is not in contact with that block. So if you're wanting to, right, that is like your gut, and sometimes it's gut versus brain, and we have to be able to overrule our quote unquote intuition, which doesn't have this kind of analytical training, right, with our analytical brains. So that's why I think it's so valuable to know that like you get your one invisible force. On top of that, no magic, no fairy forces, nothing. It has to be in contact with the body. Okay, so we've got our force stuff down. I'm going to put our sign conventions on here. I'm going to have positive in the direction of acceleration, so rightward. And then for the vertical, it doesn't matter as much. We don't have acceleration. I'll just choose upward positive there. And then we're ready to go into Newton's second law. So once we write our Newton's second law statement, I mean, from there, it's like just algebra and then you're done. So I want you to really focus on the force identification and free body diagram. Like 85, 90% of your physics happens right here in this conversation we've just been having, right? It's not about the algebra. The algebra is important. It's you have to be able to execute the problem. But it doesn't matter how good your algebra is if your forces are not identified correctly. So let's go through and some forces. I'll start with horizontal and I'll just do these in order of using the 2m and 3m block. So if I look at the 2m block, my x forces, I have F sub s equals 2m times a. That's my acceleration in the x. It's the only acceleration in this problem. There is no acceleration in the y or in the vertical. And then if I do my 3m block, I can scooch that over closer to where that free body diagram is there. That actually, I'm going to need a little bit more space. F prime, that's my positive x, right? Minus F sub k minus F sub s is equal to mass, which is 3m, times that same acceleration. Remember that we want these blocks to be staying together. We don't want any slippage with respect to each other. The nice simplification there is that that means their accelerations are the same. So that's my x equation. I'll box those for both of these. And now I can render a y equation by analyzing the y, right, for each of those. So at the 2m block, if I look at that, I've got n23 minus 2mg is equal to 0. Nice and simple. A little bit more complex for the 3m block, n sub 3 minus the weight of that block minus the other normal force equal to 0. And those are the four equations I have to work with. So this is a place you can count your equations, count your unknowns, make sure that you're good to go with your algebra from here on out. But this is kind of how we would proceed. The other piece that I would bring up at this point, I'll change colors to do this, is remind us of how we can solve for these, how we can relate the frictional forces to the frictional coefficients, of course, right? So I'll say here where F sub S is equal to, now be careful here. Which normal force do I use? Our general equation is just that F sub S is less than or equal to mu sub S times the normal force, and then F sub K is equal to mu sub K times the normal force. And I can just say the normal force as I'm talking about the general equations, but you see that it gets a little trickier in the application because we have two normal forces here. So really, really important to focus on the normal force that relates to the same interface as the frictional force you're working with. So this frictional force, F sub S, is the particular interface this acts at, is the interface between the blocks. So I need to use, here's my frictional coefficient, mu sub S, and I need to multiply that by n sub 23. That's the normal force that's relevant for that frictional force. And for my kinetic frictional force, mu sub k, which is one of our givens, and that gets multiplied by which normal force. So think about which interface you're looking at here. The kinetic friction is at the interface between the block and the substrate beneath it, the 3m block and the surface beneath it. So that tells me that I'm using normal force n sub 3. So this, again, at that interface down here, this is where n sub 3 is acting. This interface between the blocks, this is n23. So if it helps you, label it on your diagram as well. Our brains love that stuff rather than just like lists of symbols written on a paper. Okay, so I think that's all you need in order to solve for this one. And then your one unknown would be the static frictional coefficient. What you should get as your result here for the static frictional coefficient is F prime over 5mg minus mu sub k. So that would be your final expression, all in terms of givens. The algebra details for one path, again, you don't have to follow my algebraic path. Algebra is very personal. But if you would like to see it done all, one particular shot at it, then please consult the written solutions.